So this is forward, this is back. You don't need those two guys.
All right, so we're back. Now we have yet another change. We're just going to retract, go back to what was originally planning to happen. You heard a lot about the importance of async from Miho and company. Here is the gentleman, Dion Brewis, who's implementing the await feature in Visual C++. He's going to take us through what that means. Thanks, Dion.
Hi, my name is Dion Brewis. I'm a software engineer on the C++ front-end team, and I'm one of the designers and the implementer of the await feature. We can keep this talk fairly interactive, so if you want to raise your hand during the talk, I'll stop and answer questions. So first of all, I'd like to talk to you about two working group papers that we're presenting. The one is some additions that we need for Std Future, which is the ability to continue a feature when it's done. Currently, for a feature, you have to block and wait for it to be done, so you say future.get. We're proposing a change to that so that you can say future.then followed by a continuation callback. And on top of this, we're building resumable functions in another working group paper. And I'll talk to you a little bit about that today. So first of all, my entire slide deck is going to be based on PPL. I'm going to show it as in terms of PPL. The Microsoft implementation of Std Future is actually based on PPL. The reason I can't show you Std Future is because we need some extensions to the standard first for a way to work on top of that. So, but in your mind, you can translate wherever I say concurrency task, that's Std Future, and whenever I say concurrency create task, that is Std async. Okay, and as I said, it requires N3721 before we can actually do this on top of Std Future. Okay, so first of all, let me talk to you a little bit about the motivation for await. So I'm going to go over the simple case of opening a file, or opening two files, getting the sizes of those files, summing them, and returning them as a result. Now, in a synchronous way, this is fairly simple. You would say open file 1, and that returns a task back. And open in this case is an asynchronous open call. So I don't get a file handle back. I get a future back or a task back that says sometime in the future this file is going to open whenever the HTTP request is done or whenever the disk has come around to spin to that position. That file will be open some point in the future. It's not open right now. So that's why I'm getting a task that I can wait on or continue on rather than just saying this is the file handle. So I'm opening two of those guys, and then I'm blocking my thread saying, okay, fine, I don't have anything else to do. I have to now wait for the result. I have to wait for this network operation to complete. And that's what get does. So I can say f1.get, and now I have a file handle, and I can say size. f2.get, that gives me a file handle, and that gives me the size. Now the problem with that is we've created these asynchronous APIs for a good reason. We don't want to block a thread. If this is a UI thread and you do this, you're going to have an unresponsive UI. If this is a server and you do this, you're going to burn a thread just waiting for something to happen, although the CPU could have gone around and done something else at that time. So a few years ago, we created the Parallel Platform Library, or PPL, that allows you to more easily interact with asynchronous APIs like this. So in the PPL world, I would say, again, open file 1, open file 2, and I can then say, when file 1 is open, do something else. And in this case, when file 2 is open, now I can go, I have the two results available. When I call get now, it's not going to block the thread anymore. And now I can have my sizes and return this to the user. Now, as you can see, file sizes itself is an asynchronous call, because when you call file sizes, it's not going to block. It's going to return a PPL task out. So that's kind of the thing about asynchronous programming. It's very viral. Once you start using asynchronous programming in one place, you itself becomes asynchronous, your callers become asynchronous, etc. Now, await makes this a little bit easier. So if we look at the await example, that's actually pretty close to the original synchronous example. But instead of saying block, we say await F1 or await F2 instead of saying F1.get and F2.get. Now the code looks very similar, but it actually executes very differently. You can see that the return type of file sizes is a size t. The return in the first case. In the bottom case, the return type is a task of file of size t. So in the bottom case, when I call this API, it doesn't give me a result back. It promises to give me some results sometime in the future. And that's what await does for us. So when you hit that first await expression, your file sizes function at this point will pause. It will return the task to the user, and the user can then wait on the task. When that file is now finally open, the network has given me a result back. It then executes that file sizes again on a different thread. When I have a result back, it waits for the other file. Only when I have all of the results back does my caller now have the ability to get the size t result. Yes?
Yeah, your bottom left thinks it's .then plus await, but I don't see the .then.
I'm sorry, I couldn't hear.
The left, the thing that says .then plus await, I don't see a .then in that second one on the left.
Oh, I see.
I just see await.
Right, it is a PPL. It should really say PPL and await. The await calls a .then under the covers there for you. You don't see it. It's really done on behalf of you. Sorry, the slide should have said PPL plus await because it's still using a PPL task. Okay, so you can see this is a little bit simpler, but it's not the end of the world writing the right-hand side code. You can do this. However, let's take it one small step up. We read a file in chunks. So we read a few bytes, append it to a string, read a few more bytes. Left-hand side is very obvious what it does. It just whiles over the file. How would you do this in an asynchronous way? Now, it turns out this is actually extremely tricky. We can't just cycle over the file because every time we have a chunk available, we don't actually have a chunk. We have a promise that we'll have a chunk in the future. So every time after a chunk, we have to post another continuation callback. So we have to say, take the chunk, and at the end of the chunk, post a continuation, and then post a continuation at the end of the next, and then post a continuation at the end of the next chunk. You can't actually do that in a loop because a continuation is a new function. So it turns out, in order to do that, you change your loop into a shared pointer of a std function, which you give a lambda that you pinned yourself into. So you change your entire loop into a recursive function. This is not ideal. I mean, if you look at the right-hand side code, it's kind of sensical. You have a std function there. It does a .then. Inside the .then lambda, it says return next. Next is another one of these std functions that it pins upon itself. At the end of the recursion, you do a task from result, append it together, and then you go and kick this off by saying return next. That's one loop. Imagine a branch in a branch in a loop, etc. PPL, after a little while, becomes one of those things that you need to be a PPL developer in order to understand PPL code. I mean, a PPL library developer. Await, however, allows you to write it in exactly the same way that you would do synchronous code. You'd open the file, loop over it, and inside the loop, you would just do await as if it was synchronous code. The code on the left, the then.await, gives you exactly the same functionality as the code on the right, as the PPL code, but it doesn't block the thread. It will wait for a chunk. When the chunk comes in, it will schedule a new task, wait for that chunk to come in, schedule a new task. But it does this as if you were writing synchronous code, and you don't actually have to worry about all of the pending actions that you have to do yourself. Okay, so how do we actually implement this? How do we do this for you? Because you can imagine doing this type of thing in a library isn't really doable. You can't write a library that does await. PPL, or state future, represents the state of the art of what you can actually do in a library for asynchronous programming. So there are two await implementations we were looking at. The first one, if you're familiar with C#, is what's called iterator-based coroutines. Now, what C# does is, in order for these functions to be able to suspend in memory, it can't have any stack variables, because the moment you have a stack variable and you suspend this function and you return it, that stack is wiped. So what C# does is it moves all of these stack variables of the function over to a heap block. And then it rewrites the function logic that says, okay, when you enter the function the first time, it's fine. When you await it, it returns the function. When you enter it a second time, there's a big if statement in the beginning of the function, say, where was I lost? So it says switch, last position, jumps to there. And if you're in the middle of a try block, it has a switch for the last position, jump to the try block, switch for the last position, jump to the next try block. So that creates a state machine-based implementation of a function, but it does rewrite the function logic. So all of the optimizer code doesn't really work the same way, so it does change the function. In C++, we've gone a different way. We don't actually rewrite the function logic. We keep the function logic as is, and we change the execution model of the function. So the way that we do that is by running a function on its own stack just for the duration of that function. And that means that the function logic remains the same. The optimizer can do the same job with the function. Nothing gets rewritten. When we jump back into the function, we simply say jump into that position of the function, set the instruction pointer there, continue running. Because the function has this true side stack, it needs to have a little bit of a context switch there, but it turns out that that's actually a lot cheaper than rewriting the function logic itself. Okay, so let me give you an example of that. So if you follow the code on the left, I have a call sequence here of foo calling async bar, which doesn't await on async work, so it calls async work, which doesn't await on a create task. So there is a task that runs a long-running CPU task. You shouldn't really do this with CPU tasks. This is more meant for I/O, but it's better to fit this on the slide of a CPU task. So I have my normal thread, and at some point on that stack, I'm calling foo. Foo then calls async bar. For async bar, we create a side stack just for that function. A stack doesn't execute, however, so we still need to have some or other thread assigned to that stack. So what we'll do is we'll take this current thread, and we change the stack pointer and context registers and move it over to that side stack. Okay, so then we have async bar executing on that stack. That can now call some synchronous calls as if it was a normal function. And at some point, it may await again. And in this case, it'll await on async work. Again, that creates another side stack for async work. On there, we go and run the async work frame. This can call some synchronous calls in there. And then it goes and say, await create task. Now, this create task isn't ready. So you don't have a result ready for this. And it just suspends its task. So it's going to wait for this long-running operation inside this create task on the left to complete. Okay. At this point, async work returns. So it pended this task, and it's not done running logically from a logical perspective inside this function, but it already returns a task so that you can continue running the rest of your code. We're now back in async bar. Again, that awaits, and async work isn't ready. So again, it returns a task. Now, by the way, if async work was ready, in case you executed something and there's a prompt response, think buffered I/O, it'll return immediately. It won't actually pend anything. There is already a feature in PPL that says, is the result available immediately? And we're proposing in the other working paper to do the same thing for Std future. our thread is now back inside the foo function. So now we have this task of bool return that we got out of the side stack. We can continue running other functions because we just have a task. We're not waiting for the bool result. We have a promise that it'll be there in the future. So we can continue running the rest of our code. Now imagine if this was a UI function. This means you can spin a message loop. So you can run all of this on a UI thread and spin a message loop and continue running. Now, what happens in this case, however, is foo calls a blocking function. It calls t.get. Now, that has to block the thread. You're calling get explicitly, that's going to block the thread. At some point in the future, however, this long-running operation is going to complete. And the first thread is now blocked. The long-running operation is complete. And we really want to make progress on async work, but we can't use the first thread anymore. So what PPL will do is it'll proffer a new thread for us. So this is our second thread. This new thread now enters async work. Now it's very important because what actually happens is async work up to the create task function ran on one thread. It suspends. Now when it resumes, it's running on a different thread. So with a resumable function, you can actually have thread switches running or happening halfway through your execution of a function. It is a bit jarring at first. It's no different than what happens with PPL task or a state future, except that you do this over a lambda boundary. So over a lambda boundary, it's a little bit more easy to rationalize that there's going to be a thread switch. But we do feel that the benefit of the programming model still outweighs the downside of having a thread switch in the middle of a function. Okay, so async work is now done. It can now return a value. When we return a value, it unblocks async bar. Async bar was waiting for async work. Async work is done. Async bar can now run. Now similarly, it can go run some more code on a thread that it just got. And in this case, because we don't need the thread anymore that was inside async work, we can move that thread over to async bar and start executing using that thread. This is actually something that PPL does for you already. Now at some point, async bar is going to complete, it's going to return true. And now we have our result back on the main thread. So the main thread was blocking in this case. It gets the result back and can unwind the stack. Okay, so I'm going to go over to in a demo, but before I do that, do you have any questions about this execution model? Yes?
Don't you think that such a clever manipulation with stack will drive like dynamic analysis and antivirus software completely crazy?
So the question was, do we think that a clever manipulation of the stack like that will drive dynamic analysis software completely crazy? It's actually the asynchronous programming model that already drives dynamic analysis software crazy. It's one of those unfortunate things, and especially if you work in metro applications where everything is asynchronous. Even if you use PPL on top of that, you're going to have most of the pitfalls already. But yes, there are some additional pitfalls that come into play. For example, the debugger isn't happy with you switching a thread out underneath a function. So we have to go and teach the debugger to be happy about that. So I do agree that there are some additional tools that will need to come online to really help out here. C# did a good work in getting their entire ecosystem friendly for await, and we'll have to do something similar in C++ as well. Yes?
Looks like the stack is getting fragmented. So you get new segments of memory, and become new stack. So how does this affect performance?
So the question is, it looks like the stack will cause fragmentation, so you get new sections of memory and functions run on top of that. How does this affect performance? So typically what happens is there are two cases for asynchronous programming. There is the WinRT case You click on a button, that's an asynchronous operation. You open a file, that's an asynchronous operation. You read some byte from it, that's an asynchronous operation. You write you get the buffer and move it to the text block, again another asynchronous operation. But in essence, it's one operation following another one, following another one, following another one, following another one. And really all that you want to do is at the same time you spin the message loop so that you can update the UI. In such a case, you really only have two stacks. You have your main stack, and then you have 4K extra for your side stack. If you do a lot of work in there, it can grow up to a few hundred K. But it doesn't impact localization of variables that much, locality of data that much. If, however, you have a socket operation, like you're creating an HTTP server, you're waiting on 100,000 sockets, any one of them can come in, pen an async operation, that is a different story. At that point, I would agree with you. By doing this side stack, every async operation itself potentially has the ability to create a make of memory or use a make of memory to run that operation. If they all come in simultaneously, you're going to blow through potentially a gig of memory where it could have gotten you a better locality. We do have something in mind for that. I don't know how much I can talk about that because we're copying it from another team, and that's not my place to talk about it. We definitely know about the issue. I don't think we'll address it for the CTP. For the CTP, it's more for the single-threaded one operation pending another one case. I don't think CTP is necessarily going to scale to the level of having 100,000 simultaneous open sockets. But it is something that we're intending on addressing. Yes? Yeah, so the question is, what will, because of there's a thread switch in the middle of a function, what will happen with things like mutex, critical section, and even in Windows, things like locale is associated with the current thread, you have a current thread locale, etc. We are looking into a few libraries that are sensitive to a wait that says, for example, the moment you go over an await, capture the current locale of the thread. Once you're past your wait, go and play back the locale. It is definitely an issue, but it's the same issue that you face in PPL. You just have a harder syntax to get there. If you look at the PPL case, okay, that's going to take about an hour for me to rewind that slide. But if you look at the PPL case, if you have a locale set up on the right-hand side, between F1 and F2, you then set a locale, and you then enter the lambda for that function, your locale is also lost. So similarly, you can't use a mutex in the one and reuse it in the other one, even though from a logical perspective you want to do that. I do agree that await makes it slightly harder or slightly easier to fall into that trap because it looks like a synchronous function. C# programmers have, however, been fairly productive with await, even though they have the exact same issue. And it's something that we will really have to discuss, see if we need to bring more libraries online on that. This is by no means a C++ 14 feature, right? This is still very much discussed in committee. And with CTP, our intent is really to solicit feedback on this. It's not just a matter of saying, this is what we're going to ship. And let me give you a quick demo. You'll see we're actually using unders for a change for Microsoft because we acknowledge that this feature is going to change before it actually gets mature. Okay, yes, one more question.
How are you planning to give the developer over the allocation of both the memory for the stacks and the threads? Because someone can start nesting with operation.
So the question is, do we have any plans to give the developer control over the memory allocation, the size of the stack that you get, etc.? Not in the CTP. Definitely, we know that we should. Okay, so I can give you a quick demo here. So I was planning to type in the demo, but since we're almost out of time, I'm going to use a pre-typed one. So in this case, what I have is we're including our PPL await header that basically ties await to PPL. And I have two simple functions here. The one is an adder that I'm creating a task for. Obviously, you won't do this, but it fits into the time frame allowed for me. And then I have another add function that calls the adder function twice with an await in between. So, and then I've set a few breakpoints. Now, what you can see is if I run this application, okay, let me. I'm starting in main, and main calls add 3. So it's adding 3 variables, and then I'm going to block in main to get the result of the 3. Main is running currently on thread number 5836. When I cause it to run further, it goes into the add 3 function, still running on thread 5836, and from there, it calls add 2. So going further into add 2, if I step through it, you'll see it just runs a function. I'm still on thread 5836, and then I'm returning. The moment I, however, return, I have the adder function complete. So I have the PPL operation that was pending. It completes the operation. And now I can continue running the add 3 task. So the add 3 task is somewhere in memory. It was started on thread 5836. Add 2 completed. And that task is now running on thread number 3096, which it's just an artifact of PPL because I said create task. Now, however, you'll see if I go back to add 3 is now running on thread 3096. So it was initially entering on thread 5836. It's now continuing to run on 3096. So that's kind of the thread switches that you see in the middle of the function here. Now, that's more of a side effect of what PPL does with this, because PPL in this case, we say it is a normal multi-threaded application. There's no tie to a message loop. So it has to continue running this function across multiple threads. It has no other way to do it. If you block inside the function, it has to continue it. It has to use a new thread. But let me show you what happens in WinRT. And this will apply to any UI application that uses the same execution model that PPL does. So I don't know if you've ever tried doing an open file in WinRT with PPL. It's an incredibly simple thing, but it's actually incredibly difficult to implement. So you have to say, pick single file. That's a UI to give you a file open dialog box. That's asynchronous. You have to wait on that. So in PPL, that's a .then. Open async, .then, load async, .then, reader.read string. With await, however, you just sprinkle the await and you write this as if it was a synchronous call. Now, the nice thing about this is because I'm starting on a UI thread, and specifically a WinRT UI thread, PPL knows how to execute code in there. So instead of it giving me a different thread to run, it actually will run this as if it was sequential. Oh no. I did not anticipate that. But I can show you offline on my machine afterwards if you want to come and see. But what will actually happen is it'll start this on one thread. When you await, it returns the message loop. When that operation is done, it takes the message loops and runs back into this operation, and then continue running it. When that's awaiting again, goes back to the message loop. So the message loop comes and goes into this function without actually having to use multiple threads. And in this case, you can actually use things like a mutex or a locale associated with it, because it is actually staying on the same thread. This actually makes a pretty impressive demo. It's sad that it doesn't work. Okay, do you have any more questions? Or
switching stacks in order to get these semantics makes a lot of sense.
Mm-hmm.
But I can think of a lot of other things I'd like to do with creating a separate stack.
Right.
Wouldn't it be nice also to provide that as a separate feature and expose it?
Yeah, if you actually look at this working draft paper that Niklas created, this number here in the beginning, N3722, there is a second proposal on there. The first proposal in it is awaitable functions. The second proposal is something similar to iterators in C#. I forget the name that it's using for that. But it essentially allows you to create an iterator or a state machine that processes up data as it goes along, and you can come back to the function, have it give you a result, so you can say begin and end, move through that function, and allows you to do things like do a very simple Fibonacci implementation without actually having to use recursion, just because you just proffer up results one after the other one. So you can for each through a different loop and then return it or sort and return, etc. Very similar to what C# does with iterators and yield. And he also proposes a yield syntax. That's actually the reason why C++ doesn't call this async and await like C# does. It calls it resumable because resumable is a more generic concept. We know that there's additional things you can do by having the ability to suspend a function and then resume it later. And those are two uses for it, but it would be nice that this is a general way to be able to create a state machine-based function.
But the state machine-based function is one thing, and a separate stack is a different thing. You distinguish them. I really do want the separate stack. I don't want a function you call back into.
Oh, okay. So from the separate stack perspective, we're not actually doing that inside C++. Windows is doing that. We're building this on a slightly modified fiber implementation of Windows. In Linux, you have something equivalent, which is green threads. So unfortunately, it's not a standardized concept in terms of the language itself. Maybe it should be that you can use green threads or fibers generically. Yeah, that's actually the first time we've heard that feedback. It's good feedback. Thanks. Yes?
Will the automatic continuation on the UI thread also work for Win32 applications on the desktop, or is that really not easy?
It's a PPL feature that's provided to us. I believe it will only work on an ASTA at the moment, but it is an artificial restriction. There's no reason it can't work on a desktop. At the moment, however, that's PPL behavior under Metro. Yes?
Is the modified fiber implementation used similar to user mode scheduling?
No, it's not. User mode scheduling doesn't have quite the abilities that we require. We are working with the kernel team to see if we should just modify user mode scheduling. But there are a few things that fibers can do that user mode scheduling can't do. And the one thing is you can take a current UI thread and use it to run into a fiber. You can't do that with the user mode scheduler. Perhaps that'll change in the future, but that's the current state of things. Yes?
If I throw an exception from using the function,
The question is, if you throw an exception from inside a resumable function, what's going to happen? The answer is exactly what you think is going to happen. So if you've ever done programming using either PPL tasks or StitFuture, what will happen is if you throw an exception during something that's pending, the task itself will remember that you throw an exception, and when you then say .get, that .get operation will throw the exception again. So if you extend this to await, if you have something, my talk's gone, but if you have a function, a resumable function that throws an exception, that exception gets recorded into the task. Now you have another resumable function that awaits that task. That await operation on the task will rethrow that exception in your current context.
So it went away. I don't know if it went to sleep or what, but it's there now. You want his desktop upstairs? Yeah. Okay, Charles wants his desktop up no matter what it does. Just put his desktop up.
But syntactically, that looks fair because that cause the exception cannot go south of this function.
So the question is, syntactically, it looks weird if the exception goes into the task. It looks weird if you use PPL directly or stdfuture directly. If you use await and resumable functions, you don't see it. You just put a try-catch block around your await function. And if that function then throws an exception, it translates via the task to get to your function frame, but it's all done behind the covers. So you just, inside your resumable function, you say, throw invalid argument exception. Inside your caller, you say, try await function catch invalid argument exception. If you mix and match the two, you have to say try await function or resumable function .get, and then that .get throws the exception again in your context. But with await and resumable, it happens transparently. I think I have time for one last question. There was one coming from. Okay, I'll take that one. Is there a way to control which? Okay, so with await, is there a way to control where the continuation will happen like you can do with PPL? We don't have syntax for that in CTP. What ideally should happen is PPL should give you the ability to set an ambient execution context, like C# does. At the moment, you have to specify that continuation context on the .then itself, which unfortunately means we don't have a good place in the language syntax to give you the ability to do that. But the way I envision it, the way you do that is, before you call await, you call some sort of a global PPL function that says set continuation context UI thread or background thread, and then call the await on there. Okay, well, thanks for coming. And if you have any more questions, I will be at the panel later on.
Thank you, Dion.